In this lesson, we start talking about elimination reactions. And this is where I like to say the rubber meets the road and organic chemistry really starts to become challenging. Nucleophilic substitution reactions, which we looked at previously, you can really put every case into a box. Is it going to be tertiary? Then it'll go SN1. Is it going to be primary? It will go SN2. In other words, the reaction conditions are essentially mutually exclusive. You can say that a molecule will react by the SN1 mechanism, the SN2 mechanism, or not at all. With elimination, it's much less straightforward because, first of all, as we're going to see, there are two mechanisms, but they're not mutually exclusive. And secondly, elimination and substitution will compete with each other in many cases, under the same set of reaction conditions. So we're really going to make our grid that we looked at in a previous lesson twice as big. We're going to have to consider SN1, SN2, E1, and E2. However, before we get that far, let's look at the definition of what an elimination reaction is. So, as we've discussed several times, any molecule that can be a nucleophile, also known as a Lewis base, can also theoretically be a Bronsted base. The definition of both of those types of bases is such that the same sorts of molecules will fit in to both categories. They're molecules that have lone pairs. It's just a question of whether the lone pair is reacting with a Lewis acidic site or removing a hydrogen that is Bronsted acidic. So when such molecules react as Bronsted bases with either alkyl halides or carbocations, the result is an elimination reaction. So let's look at an example of an elimination reaction. In this case, we have terbutyl bromide reacting with potassium terbutoxide. Okay, what you have to know about this is that it is a strong base. It's the conjugate base of terbutyl alcohol. It is also a large base, which will become relevant in a few minutes. If you react these two molecules together, you do not actually get any SN1 substitution product. You are going to get exclusively elimination. And the organic product that you get from the alkyl halide is now an alkene. You notice it still has 4 carbons, but now 2 of those carbons are linked together with a carbon-carbon double bond. And the bromine, of course, is gone. This is called an elimination reaction because the elements H and Br are eliminated from the alkyl halide starting material. So the byproducts are terbutyl alcohol, which is the conjugate acid of potassium terbutoxide, and then potassium bromide taking care of the rest of the atoms in the starting materials as a neutral salt. Okay, possible mechanisms. Well, there is an E1 mechanism and an E2 mechanism for elimination, just like there's an SN1 mechanism and an SN2 mechanism for substitution. The E1 mechanism is a 2-step mechanism with a carbocation intermediate, just like the SN1 mechanism is a 2-step mechanism with a carbocation intermediate. The E2 mechanism is a 1-step mechanism with no observable intermediates, just like the SN2 mechanism is a 1-step mechanism with no observable intermediates. However, as I already alluded to briefly in the introduction to this topic, unlike nucleophilic substitution where the two mechanisms are mutually exclusive, some molecules can undergo elimination by both the E1 and E2 mechanisms. And the example reaction that I put up here, the reaction of terbutyl bromide with potassium terbutoxide, is one of these cases. So this will give us the opportunity to look at both the E1 and then the E2 mechanisms in a little bit more detail. Let's begin with the E1 mechanism. So for an E1 mechanism, just like the SN1 mechanism, step 1 is the same. loss of a leaving group to generate a carbocation. Heterolytic cleavage of the carbon-bromine bond generates the terp-butyl cation, and Br- is expelled as the leaving group. Now, here comes the difference. And notice in step 1, the potassium terbutoxide was not present at all. Step 2 now is when potassium terbutoxide comes in, but instead of attacking the cationic carbon as a nucleophile, it goes after one of the beta hydrogens. It deprotonates the beta hydrogen, so we're doing a Bronsted acid-base reaction, and then the electrons from the beta carbon-hydrogen bond are transferred down to form a carbon-carbon pi bond, which ends up forming a carbon-carbon double bond. This is how we get the alkene product, and of course the byproduct is the conjugate acid of terbutoxide. So let's look at some features and notes about this mechanism. So first of all, as you can see, the carbocation is a strong Bronsted acid. It is positively charged. We've seen a lot of strong acids as being molecules with positive charges, and this one's not an exception. We generally think of a carbocation like this as having a pKa along the lines of H3O+, definitely a negative pKa, which makes it a strong acid. And the beta hydrogens are the ones that are acidic. Only the beta hydrogens are acidic. If there is an alpha hydrogen present, that means a hydrogen on the carbon bearing the leaving group, it is not acidic. If there are gamma hydrogens present, in other words, if the molecule is a little bigger so that there are more hydrogens out there, if one of these chains instead of being methyl groups was something bigger, the gamma hydrogens are not acidic. It is only the beta hydrogens that are acidic, and the reason is because the electrons left on the beta carbon after that hydrogen is removed can come down and form the double bond between what's previously the cationic carbon and the beta carbon. Okay? Under no other cases can you form that double bond because the beta carbon is a carbon next to a carbon that is only forming 3 bonds, and therefore the carbon that's only forming 3 bonds has the ability to form a 4th bond. In this particular molecule, there are 3 methyl groups on the central carbon, and all 3 of those methyl groups are identical. As a result, there are 9 potential beta hydrogens that can be removed, each methyl group having 3 beta hydrogens. And in this case, no matter which of those 9 beta hydrogens you decide to remove, you will end up with the same product. That's not going to be true in every case, and in our next lesson, we'll look at cases in which the molecule is less symmetrical and try to figure out which beta hydrogen will be removed under different reaction conditions. But that's next lesson. Furthermore, since this is a carbocation mechanism, the alkyl halide must be conducive to forming a carbocation, a relatively stable carbocation. Therefore, it needs to be tertiary or resonance stabilized, and the solvent must be polar. So in some cases, important cases, the SN1 mechanism and the E1 mechanism share similarities. It is that second step that is different. All right, what about the E2 mechanism? Well, like the SN2 mechanism, the E2 mechanism is a one-step mechanism. And if you're bookkeeping with curved arrows, which you need to be doing if you're writing correct mechanisms, the E2 mechanism requires 3 arrows in the same step. Okay, we have not yet seen any reactions that require 3 arrows in the same step. We've seen that the SN2 reaction requires 2 arrows, and a Bronsted acid-base reaction requires 2 arrows. But all of this is happening at the same time. The base is pulling off a beta hydrogen. The electrons in the beta carbon-hydrogen bond are forming the carbon-carbon pi bond, and then at the same time, the carbon-bromine bond is cleaving heterolytically to expel Br- as a leaving group. It is important that everything happen at the same time, or else you could potentially end up with a carbon that has 5 bonds to it. So steric crowding in this case is not a problem like it is in an SN2 reaction, because the beta hydrogens being removed are closer to the periphery of the molecule. A tertiary alkyl halide will never undergo an SN2 reaction. But as we are seeing here, a tertiary alkyl halide can undergo an E2 reaction, because what has the O- in the base simply has to bump into one of the hydrogens that's on the outside. It doesn't have to wiggle its way in to the back side of the carbon containing the leaving group. So the E2 mechanism is possible with primary, secondary, or tertiary alkyl halides. It is not possible with a methyl alkyl halide, because methyl alkyl halides do not eliminate at all. They do not have any beta hydrogens because they do not have any beta carbons. Okay, being an E2 mechanism that does not have an intermediate with a full positive charge, this reaction does not require a polar solvent. It doesn't care if the solvent is nonpolar or polar, although a polar solvent is just fine. But most importantly, the E2 reaction requires a strong base. Because unlike the carbocation, which was a strong Bronsted acid, the neutral alkyl halide is not a strong Bronsted acid. Terbutyl bromide is if you put it into solution, is a neutral molecule, not a positively charged or acidic molecule. So this now begs the question, what do I mean by a strong base? Well, as a rule of thumb, a base needs to be at least as strong as OH- as hydroxide in order to be strong enough for E2. And how do we know how strong of a base hydroxide is? Its conjugate acid is water, and water has a pKa of 15.7. So bases that are at least as strong as hydroxide are strong enough for E2. Well, once we've looked at this, that then begs the question, well, is there any requirement for base strength for the E1 reaction? And it turns out that there is, although the requirements are less stringent. E1 reactions do not require nearly as strong of a base. And my rule of thumb, once again, is that any base that is at least as strong as water is strong enough for E1. Now be careful. I'm using water and hydroxide as kind of bookends here. Hydroxide is a strong base. Its conjugate acid is water. Water is a much, much weaker base. Its conjugate acid, in other words, what you have to look at on the pKa table, is H3O+, and that has a pKa of negative 1.74. So any base that is at least as strong as water is strong enough for E1. So what that leaves then are the very weakest bases, such as Cl-, Br-, and I-. The conjugate bases of extremely strong acids are not strong enough to even do the E1 reaction. So if one of those anions is present as the nucleophile, it will only do substitution, and you do not have to worry about elimination. Okay, as you can probably tell, there's a lot more that we have to discuss involving elimination reactions. So as promised, in the next lesson, we will talk about what happens when you have a less symmetrical alkyl halide, and there are different elimination products possible. And then after that, we will start to consider when do you get substitution, when do you get elimination, and fill in the bigger chart having both the SN1, SN2, E1, and E2 mechanisms. So stay tuned.